Hello. Okay, so someone reminded me that I completely forgot to do this. So I did a little overview of the InfoSec Battlebots arena, the sort of hardware behind it and all that. And I said I was going to do a video on the code, and I forgot. So this is it. So there isn't too much to it. This is all using sort of common web frameworks to create this thing. It's all written in Python for the most part. I do have a setup shell, but we'll go for that. So we'll look at the API first. So actually, let's talk about the components at first. Do I have a good no, my documentation is shit. So there's two components to it. Okay, there's an API which is actually doing all of the heavy lifting, and then there's a web app. So there's a front end and a back end. Very common developmental practice. In this case, the API is just another web interface that's servicing the functions, the things that need to happen on the Raspberry Pi to make the hardware do what we need it to do. And then the front end is just making it pretty and accessible. And this is where one of the vulnerabilities actually exists. But I'll talk about that as we get there. So what we'll look at here is the actual API itself. Let me move this over here. Again. So I'm using Fast API. It's a Python library that is made for making APIs. Easy as that. Okay, it's a very, very basic framework. It also doesn't support a lot of authentication and a lot of security features and that, which is why I wanted to use it, just because it is inherently a little bit insecure, because it's not made for like production environments. It's not what it's there for. So I'm using it. This middleware.cores. This is because whenever I'm calling the API and the web interface are on the same server, or the same Raspberry Pi. They're effectively the same server. So whenever the API is calling, or sorry, whenever the front end is calling the API, it's doing a local call. Okay, so it's calling the same system. For security reasons, a lot of web frameworks and things like that don't let you do that. The reason being is that they don't want, a website that you go onto, say you went onto google.com and Google tried to call something locally on your machine. That's not good. That's suspicious. That's not something that we want to happen. And so there's protections in there to stop that. That whenever you go to a malicious site, it can't immediately start collecting information in your file system. There are ways around that, but that's maybe for a hacking video. So this cores middleware, all this is just to allow me to set that, say that's okay. Functions is where we're storing all of the code that we've written, so don't worry about that. Here we're just instantiating the Fast API class into app origins. Where can we access this API from? Okay, first security point here. That's a star. So we can access this API from anywhere. So anyone on that network could call this. If I wanted to make this secure, and what I should do is limit this to only the Raspberry Pi's IP address, and that way only it can communicate with the API. Okay, something to bear in mind, anything can call this API. Here is the cores middleware stuff. This is just bog standard, copied and pasted from the interwebs of their config pages. And here we have all of the API calls, and so you'll see here we've got root, which doesn't go anywhere, just get a message, what are you doing? And we've got /pit, it returns, it calls the pit function, and then just returns a message in the console. It's just logging, saying the pit was triggered. Flipper, spinner, the spinner has the same function, but it has an on-off call, so whether it's on or off. That looks like I've actually got a typo in there that I've got on of. Interesting. So if it's that, it turns on. If it's anything else, it turns off. So actually the spinners weren't working whenever I was doing the workshop, and I wonder if this is why. So that could be interesting. Oh no, it's not. Sorry. Okay, yes. That's just what, yeah, I remember now. So on off It's just saying whether it's on or off. It's a Boolean value. I'm not even able to read my own code. This is why comments are good in your code. It's a Boolean, so it gets a true or false value. So if on off is true, so it's if true, spinner on, else spinner off. Past Grant didn't make that clear. Then we've got the start match. That starts the timer and sets a flag, which we'll talk about in a second, and then stop. Okay, so that's it. So that's all the endpoints. That's all of the URLs that we can navigate to call something. What we're actually calling, if I go into functions, is this stuff. So our imports, we're getting time sleep so that we can do timers. We're importing the Raspberry Pi GPIO stuff, all fairly standard. And then sys and logging, because we want to have good logging. If you're making any kind of web app, any kind of framework, anything like that, do logging. Okay, do it from the start. It will save you so much time later on. So we have basic logging. Another thing to note, here's the file path to the logs. That might be helpful if you were trying to attack this system. So got the path to the logs, our encoding, that's fine. Our debug level, that's fine. This is a little bit of formatting. So we want the date time stamp, whether it's debug info, whatever, a couple of spaces, and then the actual message itself. Okay, so it's just format. I like that format. There is some defaults you can put in there, but I just personally like that one of timestamp level message. And then here we're just setting up the GPIO. So if you remember from the hardware, the Raspberry Pi was all hooked up to a series of relays. And those relays then went to the physical component that needed activated, whether it was the solenoid for the flipper, the pit, whatever. This is just setting up the GPIO pins that go to those relays. So in this case, they are pull up, I think. I can't remember. I think I said it in the hardware video. They are one of them. Actually, I don't think they're pull up at all. Are they? Doesn't matter. Either way, these set these basically are set to 0, and whenever they get turned on, they go high. Whenever they go high, it then turns on the relay, which then is basically like a switch that turns everything on. So that's just setting up the pins. This one I did comment because it would get very confusing very quickly if I didn't remember which pin was which. Active flag. Okay, active flag.txt. This is an important one, and also an important thing if you're ever at one of our events and you're hacking the arena, do not touch this flag. Okay, this is a safety feature to make sure that whenever I'm in the arena, no one can turn the weapons on. Okay, I've hit the button a few times and the flipper has nearly broke my finger more than once. So this is a safety feature to make sure that if there's not a match currently ongoing, there's a flag in here that's set to 0, which means the weapons are inactive, and it's one of the things that we check whenever we're going through. And whenever you press the button to engage the flipper, do the pit, whatever, it checks that flag first. If that flag's set to 0, it does nothing, it just breaks. So that is one flag. Another safety feature that we're going to be adding in here is a latch on the door. A magnetic switch, reed switch on the door, so that whenever the doors open, that also is a value. So that one we can do actually from hardware, in much the same way if we have relays set up here, we can have a GPIO set as an input, and then have the wires going down into that, and so that it's hardware set. If that pin is pulled low, disconnected, then don't do anything. So we're setting that up as well. But for the meantime, that's this one. So important one, don't touch that if you're hacking this system. And then we've got our functions that we're calling, and these are the functions that the API is calling. So you can see is first of all, we've got the flag check. That checks if the flag is there. If it isn't, it just ends. I'll show you that in a second. And then it sets the GPIO 11, sets it high, logs that it was triggered, sleeps for a second, and then ends. Easy as that. These are all very much true, or the same. So here, if the state is equal true, so that's that Boolean value that I was talking about earlier. If it's true, checks the flag, turns the spinners on. If it's not true, then turns them off. So the spinner's the only one that actually toggles, because the rest of these are solenoids. So we want them to basically engage and then disengage quite rapidly, because otherwise they burn out. They're not meant to sort of hold in an on position. So they're just meant for, like the flipper, pushing something up, or in the pit, it's a latch. So we want it to go out and go back in. Spinners, we obviously want them to be on for as long as we want them on for, until we turn them off. So that's why this one has that sort of true false state, so that we can turn it on, and then whenever we're ready we can turn it off. Pit, exactly the same as the flipper. These three here, light start, light mid, light end. So in the arena we're going to have some LEDs, and the LEDs are going to have a specific pattern of, the 3, 2, 1 activate. So they'll, flash 3, 2, 1, then go green, then go white for the duration of the fight. At the point when the pit is about to open and when the weapons are meant to activate, the weapons don't activate for a bit of time until into the match. They're not active right away. Whenever the pit's about to turn on, the weapons activate, there's going to be another like red flash sort of counting down to that, to give people a warning to, maybe get off the pit. And then at the fight end, there'll be another flash of lights on the run up to the end of the fight. Then the fight ends, lights go red, match is over. So there's a couple of things with this. As you can see, we've just got GPIO outputs here. These are going to a Arduino, the Arduino that I showed in the hardware video. And the reason for that is that the Raspberry Pi is not strong enough, or sorry, isn't fast enough to address the LEDs. However, I have had success, and I forgot about this. I have had success with the hacking box, the anti-pwn box, I think I called it, APB. If you look in that video a few ago where I was making a lab to be hacked by other people, I actually got LEDs to work in there off a Raspberry Pi, and I kind of forgot that I did that. So even though everything online says, you can't do it from Raspberry Pi, I did get it to work. So I might try that again, I don't know. But in the meantime, this is all going to a Arduino, and then that's going into some C code, which we'll see in a wee second. So moving on from that, we've then got stop match, which just writes 0 to the flag. That's how we end the matches, because everything does that flag check. So the stop match just changes that flag to 0. Whenever the next thing starts or tries to start, it'll then check that flag, and then it will end, because the flag will be 0. So that's how we end the matches, by just writing that flag. Easy as that. Flag check itself is opening the file that we made, reading the file into content. If the content is 0, does some logging, and then sys exits. The reason that we do a sys exit is because this is all asynchronous. So we can run multiple instances of all these things at the same time, and we want to make sure that it kills the timer, because the timer could be running and other stuff could be running, like someone could run the flipper, things like that. So we want it that it kills the timer session completely without affecting anything else. Now obviously the flag will already be set to 0, so the flipper won't work, things like that. But we want to have that we could kill that timer session, but not kill everything, including the actual web app itself. So that's why we're doing a sys exit there. And if it's 1, then it just returns. So if we check this flag check, it checks there. If the flag is set to 0, it kills the whole session. If not, it then carries on. Easy as that. Okay, now the match timer itself. Whenever the match starts, it calls this function. Calls the match and sets the flag to 1, which activates everything. Now we will have a time sleep, or we'll move, this flag to somewhere else, just so that we want a delay. We don't want the weapons, particularly the pit, to be activatable right from the start. So we want to have a little bit of a delay before that happens. it's meant to be halfway through the match, but we found that, you know, maybe a minute in or 30 seconds in is actually a little bit more high paced, I guess. Some matches struggled to get to the point when the weapon's actually activated, so we'll be doing some fiddling with the time in there. Now, some of you might notice an issue here, and you would be right. Here we're setting the flag to 1 and we're doing the light start. If we want to set the flag further down, light start is never going to activate, because if we go up to light start, you can see it does a flag check. So if we don't do that flag right at the start, then light start isn't going to run. Okay, because we're never setting it to 0, it'll be, or sorry, we're never setting it to 1 to activate. So a little problem, but the easy way around that is to just get rid of flag check for light start, because it's always going to be the start of the match. It's always going to be the first thing that happens. So that's fine. If it runs, that's not a problem. It's also not callable from the API. So if we go back to the API, you'll see the only things that we're calling here are pit, flipper, spinner, start and stop. So even though we have these functions in functions, you know, we have them in here made, you can't actually call them from the API. So that one I think is totally fine to remove, and then we can move this further down, have light start, because before we do the pit, before we do any weapons, anything like that, we'll need to set this flag to 1. So it can be further down the chain, and it's not the end of the world if light start doesn't have that flag check in there. So that's the API. Okay, that's the back end. That's the thing that's doing all of the interaction with the hardware, with the Raspberry Pi and the relays and the Arduino and all that good stuff. Okay, it's all done from the API. A couple of things that are worth noting. If I go back into the API, there's no authentication in this. Okay, if I start this, which I'll do in a second, I can just make these calls. Okay, there's no authentication. So, like, what could an attacker do with that information? And keep that in mind when we move into the web app. So if we go over to the web app itself, we go into app.py and we're using Flask. Flask is a web framework for like some very basic web pages. If you wanted something a lot more secure or a lot more scalable, something like Django is much better suited to it. Django is a really good framework. I like it a lot, but for this one I wanted something that was really simple, not a lot of authentication, not a lot of security. Flask was perfect for it, because it's not what it's built for. It's made for, you know, very small scale projects and basic auth. You can build some powerful stuff with it, but I think Django is just a little bit nicer for doing that. So first things that we're pulling in is we're importing Flask, render template. This is because we're using the HTML template to build our front end. Cores, again, that's very similar to the cores that was called in the API. That's that stuff that allows us to reference something locally. And then we're also pulling in some basic auth. So if any of you happen to be at the workshop that we did and we're hacking the arena, you'll have seen that, you know, there was a login page whenever you get there. You'll be able to see the username and passwords for them down below. We're using this worksug, this thing, to generate some password hashes. And then here again we're instantiating the Flask, adding in some basic HTTP auth. Here, very secure. We're setting up our users and our passwords are here in clear text. Okay, so very easy to attack. This source code is publicly available, and you would be surprised how many projects there are out there that have passwords like this. I'm not joking. There's lots that have passwords or SSH keys or various sensitive information just on a public repo. So that is in there for people to abuse. Here we have our verified password, the root itself, and whether a login is needed, and then we're passing to the HTML. And as you can see, it's just called hello because I didn't change it from the hello world that it originally was. And if we go into the HTML, I'm not going to spend a lot of time on this. It is HTML. You can see here, this is the main meat of it, these AJAX calls. And these are what we're using to then send requests to the API. So whenever you click a button, depending on the button that you press, it then makes a call to the API. Simple as that. I will show you something in a wee second whenever we start this up, and a couple of things that you can do to abuse it. C code for the Arduino, nothing too fancy in here. This is this controlling the lights, and we have very basic button presses. So these are controlled again by the Arduino, by the Raspberry Pi triggering a relay, which is what's pulling these pins high or low. These are the ones that we're paying attention to, and if it's pulled low, it then runs a start function, which flashes it red for 3 seconds, goes green, waits, and then goes white. Okay, nothing too strange there. We're just flashing LEDs. And then the setup shellcode. This is a fun one. So we obviously have a lot of arenas, or we have a few arenas, and we want to be able to make this very drag and droppable as much as possible. So what this shellcode does is it installs the API and the web app into these directories here, var www html, and then this bit here, it's setting up the service file. So if any of you are not familiar with Linux, whenever you're wanting to set up a background process, you set up these service files, and they're basically like a background process in Windows. You know, if you go into Task Manager and you see all those stuff running in the background that's not actually, you know, there. Same thing on Linux. It's run as a service, and you can make your own service very easily. You just create a file in here under etc system d system, and then whatever you want to call the service.service, and then the construct of the files is really simple. So you have unit, the description of what it is, after network target, that's just some stuff to basically say, okay, wait till the network comes up. Some service information, what user do you want this to run as? This is another security thing, bad practice. This is running as root. Not ideal. Okay, that's an admin account that has very high privileges on the device. That can be abused. The working directory, so where does it start from? In this case, this is the API, and we want it in the API folder. Limit no file, I can't remember what that's doing. That was just in all of them, so I copied it. If anyone knows, let me know. Exec start, this is the important one. This is then starting or running the command to start the API, or to start the service, or what it is you want to run. So in this case, we're using Uvicorn. This is just a background processes manager. The API app, it's in here. Auto reload, that's if we make any changes to the code, it then auto reloads from there. And then that's just the host and port number. Restart on failure, if it dies, restart after 5 seconds. Easy as that. You stick that in the services, and then you run, where are we? Systemctl daemon reload. This just basically refreshes it and looks in those service files again to pick up any new ones that have been put in. And then we can start the services, and then enable basically just tells it to start on boot. Whenever you restart the thing, bring it back up. Here we've got some DHCP information. So this is, if you remember, there was a wireless access point on the hardware, and we obviously want that to be, you know, an access point. It's just an adapter. It's just a Wi-Fi dongle, but we want it to be an access point, so we need to do some configuration to basically tell it how to do that. So here we are setting it up so that it has a static IP of 80.1. That's its own IP address. And then we are setting up a DHCP range for it to be able to give out IP addresses to anyone who connects. Host pad file, this is copied and pasted from the internet. This just sets up the wireless access point. The only thing that would really change is the SSID that we want and the interface and the password as well there, which some of you will remember as well. Again, DHCP. This is in the hostpad conf. I cannot remember for the life of me why that's in there twice. It's a different config. If anyone knows why that's in there, let me know. I can't remember. And then we're restarting the DHCP services and setting everything up so that the wireless interface starts. And that is basically it. Now, I say that's basically it after I've been rambling on for about 25 minutes. But it looks more complicated than what it is. There is actually very few components in there. So let me get the services started and or get the APIs running, and I'll show you what it looks like. Okay, so I wasn't actually going to record me starting it, but I'm having issues, and I thought I would show you what those issues are. So whenever you're developing stuff in Python, it's always best practice, and I never do it, and this is a reason why. It's always best practice to make a virtual environment in Python, or a Python virtual environment, and it's super easy to do. It is literally this command down here, python-m vinv, and then a name for the virtual environment, and then whenever you've got that, you do dot, that way on Windows, arena, scripts, I think, and then activate, and then you can see there on the left, it's got a little green arena, and now I'm a Python virtual environment. Whenever you install stuff in a Python virtual environment, like you do a pip install, it stays in that environment, doesn't go anywhere else. So it's really nice whenever you're doing a project and you're not sure what dependencies you've installed, what version numbers you have. If you're in a virtual environment, you have all in there. You can do a pip freeze like this, and it will show you any other modules that you've installed. Obviously, I haven't installed any at the minute, so let's do that. So let's do a pip install unicorn. I'll go through and install all that for me. And now if I do a pip freeze, you can see that it and its dependencies have been there, and then you just copy that and put it in your requirements file. Easy as that. So spinning up these virtual environments is handy whenever you're doing this kind of thing, because then it helps keep everything clean. The issue I was having is that my normal Python directory outside of virtual environments is messy as hell. So whenever I'm installing stuff, it's going all over the place. So it's kind of difficult to manage. So what I'm going to do is I'm going to go into the API, I'm going to go unicorn, and we want to do unicorn app, I believe. Let me just double check. Google is everyone's friend. Yeah, Google main app. No, API, I believe it is. No, wrong way. So it is API. No module name fast API. I have not followed my own advice. If I go back, you will see I have a requirements.txt. I should probably install that. So it's Python pip install -r requirements, and then I'll go and get the requirements. So this is another handy thing to have, is your requirements, which then has everything that you need to actually run your code, and make sure that whenever you do that, that you actually install it beforehand. So now let's run that again. Ooh. App not found in module API. So let me see. App is there. Let's debug this. Oh, I'm in the wrong folder. That's why. That would do it. No module named Raspberry Pi. That would be right. So I need to install the Raspberry Pi GPIO. So the reason that isn't on the requirements file, which it should be, is it's installed by default on Raspberry Pis. Let me find the library for that. Okay, so it's Raspberry Pi GPIO. Live troubleshooting. What could go wrong? really as well. I'm doing this on Windows, but the whole thing is made for really Linux, so I should really be using Windows subsystem for Linux. That doesn't like that. Okay, what we'll do. Okay, to do. I'd comment out on all the Raspberry Pi stuff. Downside to having different development environments versus where you're actually meant to be running the bloody thing. So yes, the Raspberry Pi library just won't run on Windows for me for some reason. Don't know whether that's a normal thing or not, but so comment about the Raspberry Pi stuff. It's fine. We don't need it for what we're doing anyway. And I've got it running now, so you can see we're getting prompted with the username and password. Again, you've seen it's in the code. It's very, very easy to get if someone wants it. So we're going to put that in and sign in. And we now have the GUI in front of us. Now, that's fine. We know the password, but what if we didn't know the password, right? What could we do? Well, if we go to inspect and have a look at some of the scripts, we can see some lovely IP addresses already in here. As I said before, the API really isn't that secure. It doesn't have a lot of authentication. So what would happen if we just went to the API directly instead? Look at that, we're getting a message. What are you doing? Now, Fast API has quite a nice little feature. If I go to here /doc, docs, you get this page. Here, you can see all of the API references. And if we go back to the code, the API, you see I don't have docs as a slash in there anywhere. I don't have it. It's not something I've done. It's inbuilt into the system. It's part of the Swagger API that it's using, or it gives you a Swagger UI to use. And so you can access all of this. And more importantly, if I go in here, you can hit try it out and you can run it. Okay, and that's just sent the request. And of course, you don't need to do it through this GUI either. You can see here you've got a curl and it's just going directly to the IP address here. It's obviously 127 because I'm running it locally. On the actual server, it would be 192.168.80.1. So very, very easy to get around, and is a common issue with APIs where the front end might have security. In this case, we had a password, we did have some protection in there, but the API itself was completely open. It's a common attack path. It's a common thing. API security is becoming a really big thing because people have found this, that there is some stuff may be locked down, some may not, and you're able to get a lot more information via an API than you would be from a front end site because they just haven't locked it down. And there's a lot of really cool tools that let you sniff that. So that is the code in a nutshell. We're going to be expanding on this. We're going to be making lots more variations on it. This is obviously quite a basic one that's not got a lot of security. It's got a lot of flaws, which is good. We want that. We want that for training. We want that for people to have a go at who's maybe never touched security before in their lives. But we also want to step it up a little bit and have some like more difficult things that we go to security conferences a lot. We want to have some security focused stuff in here that we can put in to make it a little bit more difficult for people to get into. So my current plan is to let this go out into the wild for a bit, let people abuse it, see how they abuse it, and then fix those things, and then let it back out into the wild, see how people break it and fix those, and just do it iteratively like that, because that's how a lot of companies will do it, is they'll basically wait till they've had an issue and then fix it. And so we're going to do that and not make it proactive that I'm going to go in and build this as secure as I can. Mainly, I don't want to upset myself by seeing just how insecure my best really is, but make it more of a reactive thing. It's okay, this is how people tore it apart. let's go in and fix that. So that's why I have actually a lot of logging on this and on the Raspberry Pi, so I can see everything that's going on to make sure that I can see how people are actually drilling this apart. So if you have any questions and anything like that, put it in the comments below. There's also an email address kicking about somewhere, Discord, Twitter, anywhere like that. Ping me if you have any questions, or if there's any more information that you want on these, on the Arena code, or any code in general. I do have a lot of weird code projects out there, lots of security tools that I've built. So if there's anything like that that you want to see more of, let me know, and certainly do more of that.